Alright, on 15, here on sample exam 6, we have an equation y equals 6x squared plus x over 2 plus 3 plus 6 over x. And the question is, what are the values of x for which the graph is concave down? So ultimately, if we know concave down, we're going to have to find the second derivative here. So if we do the first derivative, 12x plus a half, and then 6 over x, keep in mind that 6x to the negative 1 would be the power form of that. So it would be minus 6 over x squared, negative 6x to the negative 2. And then if we find the second derivative, we're going to get 12. And then in this one, it's going to be plus. And again, remember this is negative 6x to the negative 2, so it would be 12x to the negative 3. So it would be 12 over x cubed. So with that being our second derivative, if we set that equal to 0, and we subtract, we're going to get negative 12, and we multiply by x cubed, and we get 12 over here. We get x cubed over here equals negative 1. We solve that, we're going to get x equals negative 1. So ultimately the point where the second derivative equals 0 is negative 1. Okay, we also know though that the point where the second derivative would have a discontinuity here at 0 too, wouldn't it? Because of the x on the bottom, this being the second derivative. So those would be the two critical points here for the second derivative, which means that what we'd want to do is test in those areas 0 and 1. And again, or negative 1 that is, so backwards, negative 1 and 0 we'll put. And ultimately, if we put something into the second derivative that's less than negative 1, we're going to get, say, negative 2 for instance. Negative 2 in here would give us negative 8. And 12 plus something negative but smaller than it is going to be positive. If we put something between those two, like negative 1/2 for instance, negative 1/2 here would give me, if I divided by negative 1/8, that'd be times 8. Negative though, so it'd be 12 minus 96, that'd be negative. And if we go bigger than 0 here, we're going to get, like say, 1 for instance, is going to be 12 plus 12, which would give us positive. So again, even though that 0 is a discontinuity, it's still a candidate for an inflection point. We have our candidates for inflection points are where the second derivative equals 0, or where the second derivative does not exist. Okay. And so ultimately, the question is, when is this thing concave down, I believe, right? So concave down, it would be in this region, so we'd say negative 1 to 0, or in the notation they have, inequality notation, it would be that one, which is letter B. So that would be qualify as an AB problem. Inflection points, second derivative. Questions on any part of that one? Alright, what else? 19. Sorry? On 16, we have, it says the area of the largest rectangle with a lower base on the x-axis and the upper vertices on the parabola 12 minus x cubed. So it's our inscribed rectangle problem. We know that the dimensions are going to be x on either direction if we draw it as such. The height here is going to be given by the function here, 12 minus x squared. So if we write the area formula here, the area formula is going to be 2x times 12 minus x squared. So again, if we draw the box inside this parabola, the x direction in either way, okay, that means the bottom dimension of that box will be 2x, x plus x. And the height, wherever we write the x to, the height's going to be determined by whatever the function is at that point. You know, again, this one I drew, it could be thinner and taller, or it could be wider and shorter, etc. But bottom line is this is our equation that we want to maximize, and when is an equation a maximum? When the first derivative equals 0 or doesn't exist would be our candidates or endpoints. And so in this case, I would multiply this out and get 24x minus x cubed, 2x cubed that is. And if we find the derivative, we're going to get 24 minus 6x squared. And if we set that equal to 0, we get x squared equals 2. Oh, 4. Subtract 24 and then divide by negative 6. And then ultimately we get 2 for our x. So x being 2, keep in mind it says what is the area of this rectangle. Just to test, if we do our 2 here, we put it on our number line and we put it into our derivative here, which is this one. So we're doing our first derivative test to make sure that that actually gives a maximum. If we put a number less than 2, like 1 for instance, we'd get a positive. If we put a number bigger than 2, like 3 for instance, we'd get a negative. We'd have 224 minus 54. And that would in fact qualify as a maximum because 2 increasing to the left of 2, decreasing to the right of 2, which would make a maximum here for 2. And then ultimately again we want to find the actual area of this rectangle. So 2 is the x value that will give us a maximum. The actual area we find by plugging it into the area formula. So if we do 2 times 2 times 12 minus 2 squared, we get 4 here. And here we get 8, which would be ultimately 32. And 32 looks like letter D. So that would be an AB problem also. It's an optimization problem. And again, the general strategy of an optimization problem is just to write an equation for whatever we're trying to maximize or minimize. Okay. Identify any endpoints if there are any. Okay. Find the derivative, set it equal to 0, or find out when it doesn't exist. Identify your critical points, in other words. And then evaluate and see what your critical points are. Make sure they're maximums or minimums, whatever you want them to be. And then from there, you go back and make sure you actually answered the question when you get done, which is what is the actual area. Okay. Questions on that one? What else? 19. Oh. 19 says we have the curve x squared minus y squared plus x equals 2. And we want to know at what point is the tangent line vertical. Right? So in other words, when does the derivative not exist? We can only have a vertical tangent if the derivative didn't exist. So if we find the derivative here, we should recognize that it's an implicit differentiation problem because we could theoretically solve for y here, but it would be a two-parter because we have y squared in there. So if we find the derivative of those 3 on the left-hand side, the right-hand side would be 0, of course. And ultimately we'd have negative 2y dy dx over here. This would be negative 1 minus 2x over here. And if we divide, we get dy dx equals be 1 plus 2x all over 2y. And we divide it by a negative 2, we can make all that positive. And again, keep in mind the question is when does the derivative here not exist? Well, if it didn't exist, then 2y would have to equal 0 then, wouldn't it? So therefore, wouldn't y have to equal 0 if that was the case? And if y equals 0, then again, keep in mind the question is at what point on the curve do we have a vertical tangent? So keep in mind that we have the y coordinate. How are we going to find the x coordinate if we know the y coordinate? Just plug it in here. So with that, we'd have x squared plus x equals 2. Got a quadratic equation. And conveniently for us, it factors plus 2 and minus 1. So we get negative 2 and positive 1. So ultimately at negative 2, 0. And 1, 0 would be the 2 points where we'd have the derivative not exist. And ultimately, is that an option for us? And it looks like letter D. So again, AB problem. Okay. First of all, it's implicit differentiation that we need to know. And then also, we need to be aware of the fact that we would have a vertical tangent only when the derivative did not exist. Questions on that one? Others? All right, how about the next part, 20 through 24? On 22, we got another looks like implicit differentiation possibility, maybe. We'll find out. It's because we have an equation given 4x squared plus y squared equals 1. which we know is ultimately an ellipse. And it says the base solid in this region enclosed by the ellipse. Well, we know it's an ellipse too. They told us, obviously. All right. And it says if all plane cross sections perpendicular to the x-axis are semicircles, then its volume is what? All right. So again, we got the region here in the plane that is going to be determined by this ellipse. Okay, and when we have cross sections that are perpendicular to the x-axis, that means we're going to have vertical cross sections for whatever the shape is. I guess step one would be here to draw a picture of this, keeping in mind that in the general form, instead of times 4, it would be divided by a quarter. If we put it in the form x squared over a squared plus y squared over b squared equals 1, which is the general form for an ellipse. And that means in the x direction, we're going to go a left and a right. So ultimately, I'm going to draw it a little bit big here. So we'll go half and negative half, and then 1, negative 1 here. So ultimately that would be our ellipse. And just for argument's sake, if you didn't remember that or whatever, you can always plot points here to get a picture of what this looks like. It's on the non-calculated part. If you put a 0 in for x, we get y squared equals 1, which means that 0x gives us positive 1, negative 1. So we get 0, 1, 0, negative 1. If you put a 0 in for y, you'd have a quarter on the right because you'd divide by 4. And if you take the square root, you'd have plus or minus a half. So we go half left, half right. And so bottom line is if we take a vertical slice as such, and we find the area of that vertical slice, keeping in mind that the area of the slice, the general shape of the slice is a semicircle coming out of the paper at us, remember? So ultimately be a half pi r squared would be the general formula for each slice. Okay? And so for our case, what is going to be the radius of our slice is the question. Okay? All right. The radius of the slice is going to be this distance from here to here, isn't it? Isn't that going to be the radius of the slice? Right. So with that said, if we were to write y squared equals 1 minus 4x squared, and then y equals plus and minus the square root of 1 minus 4x squared, the top half of that ellipse part will be plus and minus. Actually, I just want the plus 1. So if I got y equals the square root of 1 minus 4 squared. Remember, wherever we are in the plane with our slice, if we put x in there, we're going to get the height of that particular slice, which again gives us the radius. And so that right there is our integrand, 1 minus 4x squared. Alright. So ultimately, if that is our integrand, and we have an integral going from negative half to a half, take out our 1/2 pi, and we have 1 minus 4x squared as our integral because we're squaring that square root. And from there, it's a fundamental theorem problem because we don't have a calculator. If it's a calculator problem, then we just type it in, but ultimately we have to do the math on it. So if we do our antiderivative here, we get x minus, it would be 4x cubed over 2, or 3 I mean, negative half and half. Questions so far before we finish? Alright, so let's do the math on this. We got a 1/2 pi out here. We got a half minus. If I put a half in here, I'm going to get an eighth. 4 times an eighth would be a half. Half over 3 would be a sixth. So that part we'd get 1/2 minus 1/6. And then if I put a negative half in there, I'm going to get negative half minus. Negative half is going to give us negative 1/8. So ultimately we get negative half over 3 would be negative 1/6. Alright. So if we set everything up right and do the work correctly, keep in mind that the halves are 3/6. So we get, I'm running out of space here, I'm going to take this over here, don't mind. So I got a 1/2 pi. These two subtracted would be 2/6 or 1/3. Minus these two, I do plus plus. So I got negative 1/2. So negative 3/6 plus 1/6 would be negative 2/6. Which would ultimately be negative 1/3. So again, I get a 1/2 pi here. I get 2/3 here. Ultimately, that'd be pi over 3 if I divide the 2's out. Pi on top, 3 on the bottom. looks like that belongs to C. Questions on anything from that question? Ultimately, that'd be an AB problem. Cross-sectional area is AB. Anybody? Questions? Anything I did on that one? What else up to 24? There. 21, we got limit as x approaches 2 of f of x over x minus 2. And it says that that's equal to f prime at 2, which is equal to 0. All right. So with that information, we know that this limit right here is equal to the derivative at 2, which is equal to 0. All right. So in the first part here, it says that for number 1, it says that f of 2 is equal to 0. So the question is f of 2 equal to 0? Well, we know the derivative at 2 is equal to 0. And does that make the function value 0? Well, think about this. Remember that our alternative definition for the derivative, we know that this is of the form of the alternative definition where it's f of x minus f of a over x minus a. Whoops. A, general form. And ultimately, I remember all that is the y value minus y value over x value minus x value, okay, from one point to another. And the limit as x approaches, and then that's also a, sorry. The limit as x approaches a takes x and a, the 2 points in question, and makes them what? Makes them the same point, makes them close, infinitely close together, which gives us the derivative at a point. So based on that, if we look at our definition that we're given 2 here, right? And so if I were to do minus, not equals 2 on top, and I do x minus 2 here, ultimately to get to the original here, what would f of 2 have to be in order for that to be the case? It would have to be 0, wouldn't it? So therefore 1 is what? 1's good, isn't it? Alright, how about number 2? F is continuous at x equals 2. Well, the fact that it has a derivative, differentiability implies continuity, doesn't it? If it's differentiable, it's got to be continuous. Okay, that's not the case backwards. Remember, continuity doesn't imply differentiability, because we could have something like that, and it would be continuous, but not differentiable because it's continuous at that point, but it's not differentiable because it's a corner. So 2 is good. And then number 3, it says that f has a horizontal tangent at the line at x equals 2. Well, the fact that the derivative is equal to 0 would make it be a horizontal segment if we were to do it, wouldn't it? So therefore 1, 2, and 3 are all good, so that should be letter D. So again, the AB problem, definition of the derivative, and then ultimately some properties of the derivative. Questions on that one? What else? Through 24. Let's see here on 24. We have dy dx equals y cosine x. And they give us an initial condition, so it's initial value problem here. So remember our procedure with solving an initial value problem here is to separate variables. The y's with the y's and the x's with the x's. Integrate both sides. So we get natural log of absolute value of y over here. Over here we get sine x plus c. Remember, immediately after we integrate here, we're going to plug in our initial condition and find c. Initial condition is 0, 3. So we get ln of 3 here sine of 0 is 0. So ultimately we get ln 3 equals c. And we compose both sides with e, we get y equals e to the sine x plus 3. And ultimately, we got, let's see, remember that form is not any of them, and one thing you got to be careful with here is when we compose both sides with e, if you just did e to the sine x and then we put a plus 3 on the end and chose letter b, it's not going to be right, is it? Remember, the whole side needs to get composed with e, so that 3 is in the exponent, it's not inside here. So remember, this also can be written as sine x and then e to the 3, which ultimately gives us y equals e to the 3 e to the sine x. Like that. Keep in mind that that's just a constant, e to the 3. And did I miss where? Oh, it's ln 3, sorry. Actually, that makes it even nicer, doesn't it? So e to the ln 3 is just simply 3. So 3 e to the sine x, and is that an option? 3 e to the sine x? Yep, should be letter e. Alright, so again, AB problem. So it's just a separable differential equation. What else? 25 through 28. Sarah? Alright. Actually, 27 is one of that form that we talked about last week that we're not going to be responsible for. So don't worry about that one for the time being. I said I haven't found an answer to whether or not for sure that's not on yet. So until I know it's for sure going to be on there, then we're not going to worry about that. And depending on how much time we wind up with, I'm going to show you that at some point, but at this point we don't need to do it. What else? 25 to 28. On 28, we have a graph given, and it says that this line PC is the tangent line to the graph of f at point P. Points A, B, and C are on PC. Points D and E are on the graph of f. And the question is, which of the following statements are true? Right. So the choices here involve Euler's method, which of course is a BC issue. Okay. And in the first part here, it says Euler's method uses the y coordinate of point A to approximate the y coordinate of point E. Okay. So ultimately, again, with our Euler's method, remember what we want to do here. If we were given some, for instance here, this P is our guess, if you will, our starting y value. And we start out with our, actually we don't have any values, I don't believe, right? So y of P is equal to, some y value, okay? And again, you take a look at the general form again. Review the procedure again one more time. So if we do our approximations to this curve here, remember in general, the general form here is that the guess that we get comes from the y value of the previous guess. Okay. And to that, again, remember this is all this is really just a linearization here. And we're going to take f of the x and y, which ultimately is the derivative. This is just a representation of the derivative at the original point, if you will, and times the change in the step change, if you will. And again, in this particular case, how that would play out with our picture is with our if we used the y value at p, if you will, to find y1, the next guess, we would use again the y value, the y sub 0, which ultimately would be, I'm going to write y sub p, because it's going to be the y value at p, the current y value. Okay, and then to that we're going to add the derivative, which I'll leave blank for this time being, and then ultimately the this part here, the dx part here, would be the change in x, and our change in x here is ultimately I guess it's a minus p, if you will. It's the difference between a and p. It's how far we go from getting from point p to point a, if you will. All right, and then ultimately here we need, again, the derivative of our function at p, if you will. So our derivative at p is going to be what that part is in general. Okay, so let me make sure that's on the screen better for you. Okay, so again, in interpreting this procedure to the context of this particular equation, again, if we want to find y1, which is our guess, which ultimately means the y value at a, if you will. Actually, nope. We're approximating the y value of the curve here, keep in mind. So it's actually the y value at e, the next point over from p. Notice on the curve it goes PED. On the line it goes PABC. Okay. So if we want to estimate the y value of the e coordinate point, if you will, we're going to use the y coordinate of p, and we're going to do the derivative at p times the length, and ultimately the length a minus p is exactly the same as e minus p, because a and e are vertical to each other, so it doesn't really matter whether you're at a or e here. But with that said, that would be how we get the estimate for e. So based on that, again, let's look at our choices here. It says that Euler's method uses the y coordinate of a, okay, to approximate the y coordinate of e. So I guess the question is, anywhere in here do we use the y coordinate at a? And if so, where's the y coordinate at a in this picture? Remember, these are x values in here. This is the next distance. Is there any y coordinate of a here? We use the y coordinate of p, but do we use the y coordinate of a? No. So that means 1 is what? 1's out. Okay. Is it? Oh, jeez. Well, all right. Let me restate that then. Let's look at the wrong one. So, y e. Let's see. So if we wanted y at e. That's why we'd have y p. I'm going to have to think about that for a minute then, because I don't... Next y depends on the previous y. The next y depends on, this is the previous y, this is the derivative at that previous point, and this is the change in x. So in the context of our problem, if we wanted the y coordinate at e, we need the y coordinate at the previous point, which is p. Think about that one, because I think the way that we're interpreting the rule is correct, so might be missing something. I'll think about that one for a minute. How about this? Check out the other ones just to see if they're easy or difficult to rule out here. Ultimately, it says Euler's method uses the x coordinate of point B to approximate the root of the function at point D. Ultimately, the x coordinate at B so let's say the x coordinate at B to approximate the root of the function at point D. So if we wanted ultimately we wanted y of D, we would need y of A according to our prime at A, and then it would be B minus A. see. And we would need the x-coordinate for that one too, so. Yeah. What's that, Matt?
Number 2 and 3, they're asking for the root of the function.
Right, the root of the function. Yeah, you know what? I guess, yeah, the reason why that wouldn't be any good is because this ultimately gives a y value, and the root is an x value. So we could find that the y value, ultimately we should get something close to 0 if we did that on this one, because the d value is, the y of d, if you will, is 0. So that one's not okay because, again, the root is an x value, and Euler's method gives us y values. Okay. And then I guess that would be the same thing for 3. That's also a root. So 2 and 3 would be out. And so I guess the only option, if those two are definitely out, would be 1 there. I'm gonna think about that though in the context of the definition, because that's a little bit different form of the definition that we've used in the past. Because ultimately, again, the ruling out, we could get the right answer with that, which is 1 only. There's no option for none of the above, so like I said, that's really the only viable option here. I'm gonna toy around with that a little bit more, see if we can come up with a better explanation for it though, because like I said, I'd like to think that that would work with our normal definition. We'd have to make any adjustments to make that work, so I'll think about that when we revisit it later. All right, what else on our 15 through 28 group?